All right, well, thank you everyone for coming. I am excited today to share an introduction to the new NIRSpec Bots Prism multi-stripe subarrays that we'll be offering starting in this cycle. I will start off by giving an overview and introduction to Prism multi-stripe capabilities, and then I'll step through the APT and ETC and some considerations when you're designing Prism multi-stripe observations, and I'll end with some details on planned calibration efforts for this new mode. So for those of you who aren't familiar, or a refresher for those who are, NIRSpec Prism bright object time series observations, BOTS observations are taken with some common or standard setup. In particular, the sub 512 subarray is the most commonly used subarray used for Prism observations. Sub 512 is 512 pixels long by 32 pixels tall. The recommended filter and disperser combination is Prism Clear, and the prisms vector are dispersed across NIRISS1 only. I'm showing an example prism trace here in the bottom. We can see that the prism trace is straight, spans most of the sub 512 subarray, and fits kind of nicely within it. BOTS observations using Prism are most commonly taken for transiting exoplanets. Of course, that's not the only science case that can be used, but it is the most common. With Prism, we have a broad wavelength coverage between 0.6 to 5.3 microns at low spectral resolution, or about 100. And Prism observations have been taken for small transiting exoplanets, for example, TRAPPIST-1e is shown on the bottom left, and also for larger exoplanets like WASP-39b shown on the right here. Prism actually provides the broadest wavelength coverage across all JWST instruments and modes, but it is subject to this most stringent bright limits. So for targets that are brighter than the Prism bright limit of 11, we can face some saturation or partial saturation. And this is actually the case for the early release science transiting exoplanet community observations of WASP-39b, which is a little bit brighter than J magnitude of 11. I think it's J magnitude of about 10.6. And we see that there is partial saturation between 1 to 2 microns in this region. However, with the new Prism multi-stripe capability, we are now accessible to brighter targets with Prism, avoiding detector saturation. And this happens because multi-stripe enables readout of portions of the detector, also known as stripes, to go down to brighter targets while simultaneously avoiding saturation of the detector. And some of the heritage for the multi-stripe readout capabilities comes from NIRCam DHS, which was rolled out first in cycle 4. Some more information and an introduction to this mode is included in JWebbinar 35, and we'll hear some more about the status of DHS time series observations from Martha later in this webinar. But in a nutshell, DHS produces several dispersed spectra across the detectors. I will say that the way that DHS is set up and implemented is quite different from the NIRISS sauce multi-stripe implementation and also the Prism implementation, which I'll talk about later on. NIRISS sauce multi-stripe was rolled out in cycle 5 and reconstructs the stripes back into the sub 256 footprint. And there is an introduction to this mode in JWebbinar 43. And of course, we'll hear a little bit more about the status of the TSO calibrations for NIRISS sauce multi-stripe later on in this webinar as well from Aaron. So for Prism multi-stripe, the implementation is analogous to the NIRISS sauce multi-stripe. And we are offering 4 new subarrays for the multi-stripe mode, which are based on splitting the standard sub 512 subarray into different stripes. So the 4 options we have are the sub 256, sub 128, sub 64, and sub 32 multi-stripe subarrays. The names of these subarrays include some information about the stripes themselves, in particular the width of the stripes and the number of the stripes. So for example, for the sub 128 M4 _ Prism multi-stripe subarray, 128 is the width of the stripe in pixels, and there are 4 stripes in this subarray in order to step through the sub 512 subarray footprint. And the widths of these stripes in particular include both science and reference pixels. And I'll get into this shortly into why this matters and what this means for the subarrays. With these new multi-stripe subarrays, we have an improvement in the Prism bright limit from J magnitude of 11 down to J magnitude of 8 for the smallest subarray. And with this improvement of 3 magnitudes, we now have access to broad wavelength JWST observations for about 1,400 additional exoplanet targets. And so this capability really is expanding the number of targets that we can do broad wavelength science with. As I mentioned earlier, the subarrays include both science and reference pixels. In particular, we're interleaving 4 reference pixels at the start of each stripe. Which means that when we remove all of the reference pixels and stitch up the stripes together to assemble just the science pixel region, each of the science pixel regions for the multi-stripe subarrays is slightly smaller than the standard sub 512 by 32 subarray, and also each of the multi-stripe subarrays have a slightly different size relative to each other. What this translates to ultimately is a slight loss of wavelength coverage in the red compared to sub 512, which goes out to about 5.3 microns in the red. And so for the biggest multi-stripe subarray, that's the sub 256, the reddest wavelength ranges that we cover is 5.22 microns, and for the smallest multi-stripe subarray, we go out to 4.66 microns in the red. And the blue corners of the subarrays are all the same across the multi-stripe subarrays and the sub 512 subarray, which is why we end up with the wavelength loss in the red end only. If you're familiar with PRISM, you might be aware that the sub 512 subarray does not touch any of the detector edges for NIRSS1. I've got a cartoon here showing where the subarray sits in the NIRSS1 detector frame. And so there are reference pixels at the edges of the detector, as shown in the orange outline here. And since we are not touching any of the reference pixels or any of the detector edges, we want to interleave reference pixels in our multi-stripe observations in order to improve the noise and sensitivity that we have with multi-stripe. And so we have made a choice to interleave 4 reference pixels at the start of each stripe for PRISM multi-stripe observations. And so what this looks like when you're taking a PRISM multi-stripe observation is we start at the bottom of the detector, because in the detector frame we read from bottom to top. We'll read 4 reference pixels, we'll skip 1020 pixels in order to get to the blue edge of the sub 512 subarray, and then we'll read a single stripe. At the end of the width of that stripe, we'll hop back down, read 4 reference pixels, hop back up to the edge of the subsequent stripe, read that stripe, hop back down, read the 4 reference pixels, hop back up, read a subsequent stripe, and so on. What this means is your time series is going to have a bit of a non-standard format. So for example, for the 4 stripe case, that's the sub 128 M4 subarray, the sub 512 subarray footprint is split into 4 different stripes, which we'll call integrations A, B, C, D. Each stripe itself will have interleaved reference pixels at the start. So I'm showing the reference pixels in the time series in orange here and the stripes in blue. So stripe 1 will have the 4 reference pixels plus the width of the stripe. And then stripe 2 will have reference pixels plus stripe 2. Stripe 3, reference pixels, stripe 3, reference pixel stripe 4, and so on. So the first integration will be chopped up into 4 sub-integrations per stripe, and then we'll move on to the second integration in the time series, and so on. What this means is for your light curves for your time series observations, you'll have a time dependence, of course, for your different stripes, which are taken at different times, and also wavelength dependence because the stripes are reading out portions of the subarray itself. The stripes will be stitched together in the pipeline processing in the detector 1 stage to cover the sub 512 footprint. And what this means in terms of the timestamps, because the timestamps for each of the individual stripes are going to be different since multi-stripe reads out each stripe separately. When the stripes are all stitched together per integration, there will also be the median of the timestamps per integration that will be recorded. And all of these timestamps, both per stripe and per integration, are going to be handled by the JWST pipeline. And the implementation of this is going to be analogous to the implementation in the pipeline for SOS multi-stripe. Now, with these improvements in the bright limits with multi-stripe readout, we do have some sacrifices that we make with the signal to noise. And the reason for this is that when we have our stripes read out, we have shorter frame times, shorter effective exposure times, as we're only reading out a single stripe at a time. And there is light falling on the other pixels, but that light is not being recorded. And so nominally, we would expect the signal to noise to fall off proportional to the square root of 1 over the number of stripes. But in reality, the signal to noise is actually going to fall off more rapidly than this because we have several readout inefficiencies like resets between stripes, interleaving of reference pixels between stripes. And so that will cause some larger sacrifices in the signal to noise. And so really when determining the sizes of the multi-stripe subarrays and also which subarrays to choose for your science, there is this trade-off space between the signal to noise and the improvement that you get in bright limits. So we'll have some gains in our signal to noise for brighter targets because we'll be collecting more photons, but also we'll have some losses in the signal to noise because we have shorter effective exposure times and larger readout inefficiencies. And so similar to the case of the choices for the NIRISS SOS multi-stripe subarrays, we're considering here for PRISM multi-stripe the relative signal to noise for a source at the PRISM bright limit compared relative to a source at the bright limit of a given stripe of size n. And so we've got the 3-group bright limit in J magnitude on the bottom x-axis and the size of the stripe in the top x-axis. And what in the optimal case, we would expect the signal to noise to fall off something like following this purple curve. And so for the subarrays that we're offering for multi-stripe, the 2, 4, 8, and 16 stripe options, for the smallest subarray, we would expect to have the largest kind of relative signal to noise losses. And so optimally, we would expect about a 20% loss in the relative signal to noise. But in reality, the multi-stripe signal to noises that we actually get don't track with this optimal signal to noise, and instead we get something that looks a bit more like this red curve here. So we have this a bit of a sawtooth pattern. I'll talk about this shortly, but I did just want to highlight, so we're only offering 4 PRISM multi-stripe subarray this cycle. And at the moment, the bright limit improvements that we have are limited by the size of the smallest subarray. In this case, this is the sub 32 N16 subarray. And right now, this is actually the smallest possible subarray that we are able to offer, given the current size requirements for subarrays on NIRSpec. In particular, you can read about this on JDocs. There is a requirement that subarrays on NIRSpec need to have a minimum of 1024 pixels. And so when splitting up the sub 512 subarray into different stripes, the smallest we can go while also satisfying that requirement is 32 by 32 pixels. But nonetheless, with the multi-stripe subarrays that we are offering, we get down to relative SNRs that are greater than 65% for all of the subarray options that we're offering. And for all of the multi-stripe subarrays, the average relative signal to noise is about 75%. And if we consider the number of transit hosts in these 3 magnitudes of improvement in the bright limit from J of 11 to J magnitude of 8, we are actually enabling multi-group observations of over 1,000 additional exoplanet targets. One thing to note with this sawtooth pattern is that when you have targets that are at the bright limit of a given stripe size, the signal to noise losses that you have are going to equal your efficiency losses. And so for targets that are fainter than a bright limit of a given stripe size, the signal to noise losses are going to be greater. And so there are some cases where when you're considering which subarrays to use, it may be preferable to have higher resolution NIRSpec gradings and even some combination of higher resolution NIRSpec observations with another instrument like NIRISS, for example. And the choice of that will really come down to your science goals. So the higher resolution, medium, and high G395, G235, and G140 gratings don't suffer the same relative signal to noise losses and also have better bright limits. The G395H bright limit is a J magnitude of about 6.1. But of course, these higher resolution gratings don't cover the broad wavelength range of PRISM. So when deciding which subarrays and gratings to use, you'll need to balance your target magnitude and required wavelength range for your science goals. Okay, I want to step through a bit about setting up your ETC workbooks and your APT files for BOTS PRISM multi-stripe observation. So for the most part, the ETC use of the multi-stripe subarrays is identical to the standard PRISM setup. There's some more details in JWebbinar 51. I've linked the slides here in case you're interested in taking a look. If you need a refresher or are new to the ETC, there's some general ETC tutorials in the left-hand colored boxes here, and some more multi-stripe PRISM ETC specific resources that are linked in the boxes on the right-hand side of the slide. In particular, there is the JWST step-by-step PRISM multi-stripe ETC guide, which walks through setting up the ETC workbook, for example, science program number 9, which is designing BOTS PRISM multi-stripe observations for WASP-62B. You can access the ETC workbook for this example science program directly from the JWST ETC. If you go to the example science program workbooks dropdown in the ETC and scroll all the way down to ESP number 9, and you can load the example science program workbook and take a look at it. Everything is pretty much standard as you would set up a regular ETC workbook with setting up your sources and scenes, your instrument setup, and your detector setup. The main difference, of course, is that in the subarray dropdown menu, you can also see the multi-stripe subarrays as an option. In APT, again, the implementation and use of the multi-stripe subarrays is identical to how you would set up standard PRISM observation, and there are more details again in JWebbinar 51. The slides are linked here. If you need some of a refresher or tutorial on APT generally, there's a link here. And again, APT-specific multi-stripe resources are linked to the right-hand side here. This is the link to the JWST step-by-step PRISM multi-stripe APT guide, which walks through setting up the APT file for example science program number 9. And if you wanted to take a look at that file directly, you can load it from the APT proposal library. You go to File, JWST example science programs, and NIRSpec in the menu. It should be available for you. One thing that I did want to point out, just to be aware of, is if you open this APT file and you look at the science parameters, you'll see that the exposures per dither and the integrations per exposure that are listed here do not match the example science program ETC workbook. And the reason for that is that there is a difference in the definition of the total exposure time for PRISM multi-stripe in ETC versus in APT. In ETC, the total exposure time is defined per integration, accounting for the total number of stripes in a given subarray all stitched together. But in APT, the total exposure time is given per stripe. And then you'll need to multiply by the number of stripes as well as the number of integrations in order to get your total exposure times in APT and ETC to match. Neither is like right or wrong. They're just two different ways of expressing the same thing. But what this means in practicality is that the number of integrations per exposure and the number of exposures per dither that you specify will differ between ETC and APT. All of this information, the explanations of these definitions, are included in JDocs in the step-by-step ETC and APT guides. You'll see a little warning box like this that goes over what the difference in the definitions are in total exposure time for ETC and APT. And then there's also a walkthrough of how to calculate integrations per exposure and exposures per dither from your ETC outputs in order to input them into APT. In particular, for the ESP, if you wanted your observing window to cover about 9.4 hours, the ETC workbook for a single integration gives an exposure time of 1.09 seconds. And so in order to cover this full 9.4-hour observation window, you would need 30,810 integrations per exposure. For this observation, we're using the sub-64 M8 subarray, so you'll need to multiply the number of integrations per exposure by the number of stripes, in this case 8, which gives you 246,480 integrations. If you try to put this number into APT, you will get an error because APT has an integration limit of 65,535. And so in order to circumvent that, you'll need to increase the number of exposures per dither in order to stay within the integration limit. And so in order to figure out what your exposures per dither should be, you will need to divide the total number of integrations, 246,480, by this APT frame limit and round up to the nearest whole number. So in this case, that'll be 4. So you need 4 exposures per dither. And then you can divide the number of integrations by the number of exposures to get the number of integrations per exposure. So that's 61,620. And so if you put these numbers into APT, your total exposure time should be roughly 9.4 hours, which is matching what you wanted in ETC. Now, if you're designing a transiting exoplanet science program, you'll probably also want to have a sense of the wavelength-dependent transit depth precisions, which are a more useful sensitivity metric for exoplanet science. And so you'll want to use a tool like Pandexo to simulate your transit spectrum precisions. And fortunately for this cycle, for PRISM multistripe, there is support for multistripe PRISM in Pandexo. This was not the case for the rollout of multistripe and for SOS and DHS. And so this is an excellent improvement for this cycle. Lastly, I wanted to wrap up and talk about some of the future plans for PRISM multistripe and summarize what we're at so far. So as a note, multistripe has not yet been tested on sky for PRISM. And so the observed precisions you get may differ from ETC predictions. But the current scope and plan for calibration is to take darks of each subarray, wavelength and flux calibration, as well as a test time series observation of a transiting exoplanet with high signal to noise and a featureless transit spectrum. These calibration efforts are analogous to the calibration work that has been done for SOS multistripe and DHS. So in summary, BOTS PRISM multistripe readout is newly available in cycle 6. We are offering 4 new multistripe subarrays, which enable PRISM observations of over 1,000 additional exoplanet targets, and this extends the PRISM bright limit down to J magnitude of about 8. And multistripe calibration efforts for PRISM are planned for the first half of 2027.